All right, well, good to see everyone. I'm Joe. As Reza mentioned, I'm in Meta. I think Reza and I have been knowing each other and worked together since at least now almost a decade. It's been at least, yeah, about 10 years. So I'm an old school kind of AI guy, kind of a reformed computer and electrical engineer. I started my career doing VLSI design for mobile phone chips, and then kind of like found machine learning and loved it. So my title of my talk is PyTorch native RL at scale. I lead at Meta a lot of our RL infrastructure as well as PyTorch, formerly led product for our Llama models. Hopefully everyone knows Llama. The other corollary to my talk here is how we learn to finally embrace real RL. And I'll show you what that means here in a second. A little bit more about me. Yes, I lead PyTorch. I'm a core maintainer, which is a little weird for a product guy, but whatever. I founded the PyTorch Foundation, along with some other folks, sit on the board. I angel and invest a little bit into some kind of cool companies, and in fact, Infract, who just kind of launched this past week, working with Simon and Jan. Congratulations again to the team. Yeah, like I said, I've worked at just about every kind of layer of the stack, from PyTorch to the lower levels to agents now, and of course LLMs and building those at scale. I also invest with Sequoia, so full disclosure. So really quickly on training. So who's training LLMs or doing post-training of LLMs, like in the room? A few hands. Okay, cool. So when I started training models, we were basically training like CNNs and LSTMs and there wasn't really the concept of like pre-training and mid-training and post-training and RL. We basically would train a model and then we would fine-tune it. And I remember that's one of the first things that Reza and I chatted about is like, how do you, when you fine-tune, you kind of like do things like data augmentation and semantic segmentation and how do you get really like strong computer vision models that you can then apply to different applications. Today, and with this kind of LLM transformer world, we obviously start with pre-training, which is evolving. I mean, kind of like, this is the current paradigm, but evolving quickly. We move to SFT, or more like the traditional kind of like, XY pair, like, you got a supervision where you're actually annotating data. There's a lot of companies that will sell you data. Scale, of course, not us anymore, or not us, but Scale and a lot of others will sell you basically annotated data, and no one recognizes the not hot dog. Okay, fine. And then from there, basically, we thought we were doing RL, or at least we as in the collective community, we thought we were doing RL, but we were doing something called RLHF, and that's reinforcement learning with human feedback. And basically, you're training reward models. And these are essentially models that judge the outputs of your model, so you can then align it. And there was always this inner struggle with these things between helpfulness and safety. And I witnessed it firsthand, shipping a lot of models, and it was fun and kind of strange at the same time, because an infinitely safe model is actually not a helpful model at all, right? It won't answer you. But what perceived as could be like infinitely helpful is actually quite unsafe. So you kind of have to find the equilibrium, find that right balance. And then of course, where we are today is RL environments. And you can kind of think of this as the real RL, right? This is basically, we have agents acting in environments. We're looking at kind of long horizon tasks, computer use, coding environments. Games are great environments to have your agent learn. Logic, and of course these are like kind of closed loop learning. A lot of it's sandboxing, and so I of course have my Pong example there. So we have evolved a lot, and the training has not just become like, pre-training and then post-training. It's really a pre-training, mid-training, post-training RL environments, and actually even then you're starting to see, there was a paper out that just came out this week, I think it was out of Stanford and NVIDIA and a few other folks, where they're doing actually test time through the entire training process. So training is evolving, it's evolving quickly, and it's gonna change the way these agents operate and improve them significantly. So if you kind of dumb down what an agent really is, at the end of the day, it's an LLM, it's got some tools, so you give it the ability to search, the ability to call Claude Code, the ability to do these things, as well as memory. And this tool use is really the action is kind of like the action space, right? You prompt it. It has, if you give it in the context some tools that it can use, it can then take actions and go and figure out, and it'll think for a while, and it'll do things, and it'll learn. It then has these environments, and these environments are now, like, who's at an environment startup, actually? I'm kind of curious, anyone? So, like, this past year has been bananas. Like, every data startup I talk to, or even brand new startups, 2 people out of, pick a company, have built an environment startup. So environments become really critical because they actually allow us to give an agent something to go and learn. So throw it into an environment. It then has a set of rewards, or a reward and some tasks. It can then pull state and basically learn. It's kind of think of it as a skill that it's learning. And then all of that actually turns into experience that you can then train on. And so that's basically your RL training. So what we found actually is just in like the last year, I basically I stopped training LLMs and started looking at the full stack because we actually had to basically retool and rethink about our entire stack from the very bottom layers. And so number one, who uses PyTorch today? Hopefully a lot of people. Okay, good, lots of hands. So we had a really strong ecosystem inside Meta. Obviously we have a huge ecosystem inside or outside in the industry. OpenAI, Anthropic, Apple, lots of folks use PyTorch because it's a great framework, and frankly, like, once the world starts building on something, it's a lot easier to reproduce and so on and so forth. So we wanted something that was PyTorch native because it was important to us. And second, we wanted to build for scale. We are building data centers. We are investing in nuclear power. Dave, shut your eyes, shut your microphone. Lots going on, right? So we're investing in kind of at the million GPU scale because we're building super intelligence and we have a lot of products that we want to ship our models into and so on. And then thirdly, we have this world that we're building that's very heterogeneous in terms of hardware. So it's not just NVIDIA for us, it is AMD, we have our own silicon. We're deploying to mobile devices, we're deploying onto glasses, on the frames. So we actually need to live in a world where it may not just be this homogeneous kind of set of hardware that we deploy to, which is actually quite complex. And we'll get into what that means for RL in a second. And so if you actually were at the PyTorch conference late last year, we released a ton of stuff. And these projects have continued to gain momentum. In the orange is a lot of the things that we actually released. Helion is a kernel authoring DSL. That emits Triton code, which is a really cool project. Torch Comms is a comms collectives library. It allows you to run across multiple hardware. It's kind of at a near infinite scale. I'll talk about these pretty briefly. Monarch we'll talk about in depth, but basically think single controller distributed orchestration. And then Forge is really an RL library. And then ExecuTorch and VLM, of course, is for kind of edge, mobile, and server, cloud deployment, respectively. And then we built this new project called OpenM. And OpenM is a way to standardize the way you interact with environments. So what we found is, we're building environments, we're sourcing environments. No environment has the same interface. We're just spending so much time just basically refactoring and wrapping these environments. Why don't we just define a common interface? So that's what we did with Hugging Face and Unsloth and a few other folks. And we'll get into that later. So I think I hit all of this. So basically, today's focus, though, is really on this kind of deep RL piece. So I want to talk about a little bit on Monarch, which is a really fun project. If you think about pathways from Google, it's somewhat analogous to that, except it's open source, and it's, think about it as a single controller kind of versus SPMD. We'll get into it. OpenM, and then, like I said, Torch Forge. So what does RL Infra actually look like? This is kind of fun. So first of all, when we were building this new stack, number one, we wanted to maximize the RL throughput while still being easy to debug. RL is actually a pretty tough thing. Like, reinforcement learning is not a trivial thing. It's not like you throw a bunch of supervised data that's annotated at your model and it largely does its thing, and your model is going to get better at seeing or learning based on those annotations. RL can be, when you're out of distribution, for example, when you're out of production distribution, your model can actually not do well. It can train well, but then actually deploy pretty poorly. And so we thought about, how do we actually maximize this, the throughput while actually being still kind of ability to kind of build and debug and get out of the way and let you kind of explore the algorithmic space. The second is you want to basically parallelize as many environments and tasks as possible. You want your model and your system to see everything. So whether that's every language, you want to be all in distribution in terms of what's inside your infrastructure, what's outside. You want your models to generalize. And so you want to reuse basically everything. That's why you see this big trend of like forward deployed engineers, or FTEs, which is like the new thing to say. Basically, these people go and they create tasks, they create environments. They bring basically companies' infrastructure and what they have in distribution. And it allows you to RL over that. So here's what an RL system looks like. It's definitely not trivial. You have basically the environment, like I said. You have generators, which are basically inference. You can think about it. You have reward modeling, a reward system. You have a replay buffer. You have trainer. You have parameter server. You have curriculum builder. And so it's quite a complex system. And so basically what happens here is you'll have a prompt within, you generate a prompt from your curriculum builder. It then generates an inference from generated. This can be like basically like VLLM if you're familiar with that project. It will then start hitting your environment. So again, this could be code or it could be a web environment and so on. It then basically looks at, applies a reward to it. Is my reward going up or not? It then puts that information into, say, this replay buffer, which can then be, trained on, and then basically this whole loop kind of continues, right? And so basically you're constantly running this RL loop and hopefully generating good rewards that then improve your overall system. And so basically, and then you of course update the weights when you're training. And so there's I'm gonna go through kind of quickly now because I don't have only that much time, but we have three main challenges I wanna go through here that kind of hopefully crystallize this for you all. One is orchestration. Second is programming model, and the third is performance. So quickly on orchestration, this is one of the most complex systems there is in the current ML training. So basically you could have your generators be essentially on, say, CPUs, because all they're doing really is inference. You could have basically your environments running on maybe like random CPUs as well, because they're just also they're just using web and they're like doing computer use or they're generating code or whatever. Your trainer could be, for example, like running on a big cluster of GPUs. And then all of a sudden you have this asymmetry. So some of these long-running tasks in environments, like think about shopping, where it's a non-deterministic thing, where you send off your agent in an environment, even a simulated environment, it's sandboxed because you don't want to like take inventory and buy stuff because it actually impacts the real world. But it's a kind of a long-running task that is definitely not deterministic, could be running a lot longer. Computer use the same thing. Whereas training is actually is pretty deterministic. You're gonna know when you're gonna basically generate gradients and so on and train. And so you could end up in a situation basically where, I don't know, your like GPUs are sitting there like 10%, running at 10%, and your inference is running at 100% or whatever it is. And so you could basically have a pretty mismatched system. And one of the things that we've overall done as an ecosystem is moved very quickly to asynchronous RL. And that means that they don't wait on each other and you can actually maximize resources and so on. I had a bunch of clicks there, I don't know where they went. I'll get into the programming model. So programming model is the second biggest challenge. So who's actually trained a distributed model? Who's actually, okay, I know you have. Okay, so who's had to deal with ranks before? I know you have. So anyone who's used Torch, distributed data parallel, DDP, back in the data parallel days when most everything was synchronous and distributed data parallel, you basically defined your processes or your ranks, and you're basically, it was tedious, but it was tolerable. But once you get into systems that are that much more complex, where basically now you have this branchy code of else ifs, and you actually will you'll have a rank, and you will basically have ranks for your generators, for your trainers. All of a sudden you're dealing with these underlying comms collectives. It becomes really, really complex. So in this case, I have an if statement that says, if this rank, I actually have some coordinator logic. Else, I'm going to basically generate some generator. I'm going to have a rank of generators, basically, because I have an inference. I'm generating inference, which is basically just prompting the model and generating outputs, and then LSIF, basically I'm going to generate basically a trainer. And so under the hood you have all of these operations that you really don't want to dig into. It's really complex stuff. When you're talking about, especially when you're talking about multi-data center, you might be talking about like your generator here is actually running on CPUs and your trainer is running on GPUs and could be even in different places. So it becomes really, really hard. So actually, how do we do this? How do we actually figure this out? I'll talk about a solution in a minute. And then of course, performance. We have a lot of bottlenecks, as I mentioned earlier. Some of these basically, like the environment can be long running. Weight sync. So when you start to talk about, I think it was Sean from Cerebras. I think it was Sean, right? He was mentioning, how he can actually fit these models actually on the chip, which is really cool. But when you start to talk about weight sync, like when you actually have to move this amount of information across different parts of the stack, or even across data centers, or across data center even, you're talking about gigabytes, if not potentially more of data. So in this case, 70 billion parameters, that's like a Llama 3.3 model, could be around 150 gigs of data, and you actually are moving that around. And so weight sync actually can be, you could actually be bound by your communication in this case. And then when you can't fit these things into a single GPU, of course you have to shard them. So you basically are creating replicas. In the case of the environment, you could be running across GPU or CPUs. You could basically be replicating your generator across GPUs, and of course reward system and so on. And training, of course, uses the beefiest systems. In this case, I just threw out kind of an order of magnitude of 128 GPUs. So really, this becomes a pretty complex thing. Like you're dealing with all of these different asymmetries in the system, CPUs, GPUs, different size, different scale, and this any one of these asymmetries can actually create a performance bottleneck. So in the solution space, so TorchForge. So we open source. This is one of the cool things about my job. I've been with Meta now almost 8 years. As Reza knows, we open source a lot of our work. We love to work with community. It benefits us in a number of ways. We get to work collaboratively with academia, with other companies, and we gain a lot from it. And so basically, TorchForge is an RL library that really allows you to kind of write pseudocode to write RL algorithms. So what we found is the people that actually wanted to write RL were not infrastructure experts. We just wanted to give them something simple, something that was actually like very, very Pythonic, very PyTorchy, let them run things, and then handle all the infrastructure underneath. And so basically, the kind of primitive in TorchForge is what's called an actor. Basically, an actor in this case could be a generator, could be a trainer. In this case, like a generator is, again, something like VLM, and the trainer could be Torch Titan. TorchForge basically offers services, but also offers underneath something called Torch Store, which accelerates that weight sync thing I talked about. And what it does is it basically moves things in a high-speed way with low latency as well as fault tolerance. So when you're shifting weights all over these systems, basically Torch Store kind of handles that for you. And then the programming model, which I get to now, is actually Monarch. So this is a really cool project. It's, again, fully open source. And this is, calling it a distributed programming framework is probably underselling it. It allows you basically to write kind of normal PyTorch code that feels like you're writing it locally on your MacBook, but it actually could be running literally 1 million GPUs in like 3 different data centers, like behind the scenes. And so that actually is it's really compelling, I think, for a lot of folks. It's compelling for people at Meta because they don't want to have to deal with basically, what I showed earlier around, basically our standard distributed APIs. It's just a lot to manage. So the standard kind of like operation or standard component of a Monarch is basically these actor meshes. And who's like familiar with a tensor operation in PyTorch? Basically these meshes become very much analogous to a tensor. So I can slice and dice a tensor, right? Different operations. If you're familiar with NumPy, you can use NumPy and manipulate tensors. In this case, I can actually do the same kind of NumPy or tensor-like operations, but these are actually clusters of GPUs. So it becomes really, really cool. So when we put this in front of researchers first, they were just absolutely blown away and how easy it was and how it leveraged a lot of the learnings that they had over the years. It also has RDMA. So basically, Basically you can do direct RDMA operations, fast point-to-point transfers, which makes it really fast. It's fault tolerant. And like I said, it has this really nice, clean, imperative Python API. So it feels like you're basically writing local PyTorch imperatively. And behind it could be, just a massive amount of compute, and you wouldn't even know it. It just feels really natural. And we actually proved this out. Again, one of the fun parts about my job is I get to partner a lot with a lot of different companies in academia. A few of us got together, me and some folks at CoreWeave, as well as Stanford and Azalea's lab over there and Chris Ray's lab. And basically, we scaled up Weaver, which is basically a weak verifier architecture that allows you to basically take a bunch of environments together and basically bring them together and cascade them and learn from a bunch of weak to get to a strong RL result. And we scaled that up. We open sourced the code. You can see the link even in there. We scaled it up on some nice GPUs that CoreWeave provided. So definitely check that out. So lastly, on environments. I mentioned environments. There's so many startups that are out there, what's going on with environments. So some of the environments we've been doing hackathons since PyTorch conference last year. We did some with AMD, we did some with Unsloth and Hugging Face. And there's been a ton of environments that have been uploaded to the hub and that have been created as part of these hackathons. And we ourselves did a hackathon internally at Meta that yielded a bunch of really cool environments that we're training on and so on. And so I just kind of grabbed a few of the ones that I thought were kind of interesting. So playing basically Mario is kind of cool, Pac-Man. And you'd never think that these environments would be useful, but they actually turn out to be really useful for post-training and actually in generalizing your models. They help reasoning, help logic, and so on. Coding environments especially are really great, especially when you start to get into like these low resource languages. It really helps to generalize your coding agents. Here's a few others. The Wordle one was, I think it was Daniel at Unsloth actually worked on that one. Pokemon, one of my colleagues I found out is actually not the world champion, but the national championship Pokemon player from Italy. So I learned that. You learn weird things when you work with people. So he saw that and he's like, I know how to play that. Of course, trading, chess. So we saw a ton of environments that came out of these hacks and now they interface nicely with Torch Forge. And basically you can kind of scale up post-training RL, Forge, write your algorithm, and then connect them up to these environments. So last year we got up on stage, or I got up on stage with Hugging Face, and we announced this thing called OpenM. And we saw this deluge of folks come along with us shortly thereafter. Basically, OpenM is this standard way to interface it. In the words we actually hear right here is like an end-to-end framework for creating, deploying, hosting, and using isolated execution environments for agentic RL training, simple APIs. In practice, what this is very much an opinionated Docker that basically has a nice clean gym-style API. And we did it completely in open source. We did it RFC-centric, so we actually are, I think, are on our fourth RFC. It supports MCPs under the hood. You can basically use just about every RL framework out there with it. And we have so it's two pieces, really on the, I guess, left for you. Really the GitHub repo provides a spec. It allows you to see if your environment is compliant. And then it has a hub, which sits on Hugging Face. And the hub is basically like a top level thing. So think about if you go to Hugging Face, you'll see the data, you'll see models, you'll see evals, and now you see environments. And it's called OpenM. And so like I said, I think we're on 0.4 now spec. The API is very clean. It's based on, or inspired by, I should say, by the Gymnasium API that OpenAI maintained and some new folks have been maintaining as of recently. So I think step, reset, state, so very simple. And then basically, like I said, containers and MCP tools as first-class citizens. It supports now reward pipelines. And Forge, TRL, which is Hugging Face RL library, Unsloth. And there's, I think, at least 2 or 3 others, I think, that are supported. So you basically use your favorite RL framework, and you can use pretty much any environment that's available. So today, for example, there's a bunch of sample environments that are in there. Coding, games, chat. Just go to the link, and you'll see a bunch of the environments there. One of the really cool things about these environments, though, is if you upload your environment into the hub, you actually automatically get this interface. And so you can actually prompt we call it kind of the human agent interface. And what you can do is actually, in this case, we have a coding environment. You can actually prompt the environment directly as a human and just play with it. And it allows you to basically get to kind of manually explore the space, as kind of a human RL agent. And just kind of gives you a really good idea of like what the actual environment is actually doing. A lot of the environments today, for example, are pretty basic. Some of them are like single turn, maybe they're multi-turn kind of evaluations. Some of them are getting more and more long horizon. I think the more time goes by, we're seeing more and more long horizon tasks, which is really interesting. But this is really cool. You can just go there and play with an environment. And as I mentioned, a lot of the partner platforms support OpenM today, so you can go and use these environments in Lightning. Lightning, I think now merged with Voltage Park, so I think they're still called Lightning after Ash Wolf Falcon. TRL has an example, Unsloth. Does anybody use Unsloth? It's really cool. So Daniel and yeah, really cool. If you know, you know. And Art is actually now OpenPipe, which is part of CoreWeave, and then UMI. So we have some really great platforms that support it. And like I said, I grabbed this a few weeks back. There's a few more on GitHub now. And so you can basically, on GitHub you can kind of see some of the examples. So we have a really great notebook, actually. If you just want to play with RL, if you're completely new to RL, Daniel, as well as Sanyam from Meta, put a Colab notebook together. Basically, it gives you kind of 0 to hero on RL, as well as playing with environments. It's built on the Wordle environment. But basically, you just go onto Colab, use free GPU, and you can just pick up RL and start learning. So it's really cool. Just go to the GitHub and it's linked right there. So yeah, I think we're really excited about where this is going, and I think at the end of the day, we're trying to democratize the ability of RL and allow anyone to basically post-train models. It was obviously relatively easy, I think, to post-train when it was just fine-tuning, but reinforcement learning is much, much more complex. And so if we can provide the tools, if we can provide the environments, and obviously open source models are now readily available and they keep getting better. I think there's really no excuse, I think, for most people to give RL a try and actually see what it can do. A couple of acknowledgments. So I grabbed this relatively recently. You can kind of see all the companies that keep putting their pull requests up and asking me to approve them. So you can see Lightning and Stanford and most recently, I think Scalar. I didn't know them, but they're in India. Surge and a bunch of others are supporting this. So it's a really cool community. Everyone's contributing to the repo, and it's been pretty awesome. And just thank you to especially the Hugging Face team with Clem and Julian and Lewis and VB and folks. Although VB's at OpenAI now, so. That's it. If you want to learn, if you want to play with any of this, just go to meta-pytorch.org, and we have documentation and stuff to get you started. Thanks.